Hello, this is Porterville College, Physics 104B, Chapter 22, Homework. Starting with number 17, it takes 45 joules to move a 15 millicoulomb charge from point A to point B. What is the potential difference, V from A to B? So the potential difference, V sub AB, is the change in potential energy going from A to B divided by the charge, which is the work that it takes to move that charge. So that's going to be work over charge. 45 joules divided by 15 times 10 to the negative 3 coulombs, and you get 3,000 volts. Number 19. Find the magnitude of the potential difference between 2 points 1.4 meters apart in a uniform 650 Newton per coulomb electric field if a line between the points is parallel to the field. Alright, we have a diagram right here. Here's points A and B. The electric field is 650, I wrote it as volts per meter. And so as I did this, I just took the absolute value. Delta V, the voltage difference, is the absolute value of E, or the x component of E, times displacement. So 650 volts per meter times the distance, 1.4 meters, and we get 910 volts. Number 21, a proton, an alpha particle, and a singly ionized helium atom are accelerated through a 100 volt potential difference. How much energy does each gain? We're going to use this equation that the energy each gains, meaning the change in potential energy, is Q times the voltage difference. Now they're accelerated, and so actually they will have a negative change in potential difference as they gain kinetic energy. So really, as I'm doing this problem, I'm just taking absolute values because they will have a negative change in potential energy. We need their charges. The proton is plus E, the alpha is plus 2E, the helium, the ionized helium, is plus E because it's got 2 protons and only 1 electron. So for the proton, it's the plus E times 100 volts, and we get 100 electron volts. Do that conversion, you get 1.6 times 10 to the negative 17 joules. For the alpha, we have plus 2E times 100 volts. That's 200 eV, which is 3.2 times 10 to the negative 17 joules. And for the singly ionized helium, that's plus E times 100 volts, just like with the proton. It's 100 eV times 1.6 times 10 to the negative 17 joules. Number 23. An electric field given by E naught J hat, where E naught is a constant. Find the potential as a function of position taking V equals 0 at Y equals 0. Here's my diagram. Y equals 0 at V equals 0. There's the electric field. It's a constant, so E naught times J hat. It's in the J hat direction. We're going to use this equation that the potential difference between 2 points A and B is the negative of the integral from A to B of E dot dr. E is a constant because it's a uniform field, and so we'll get rid of that integral and just say it's negative, the dot product of E and delta R. And that is the difference in potential between points A and B. So let's specify here what those points A and B are. We're looking for the potential difference over the 0. So A and B becomes V of a given Y minus V of 0, which goes to 0. So we have that the voltage at any given position Y is negative E dot delta R. So we have Vy equals and we now make our substitutions. The negative of, remember the electric field is E naught j hat, dotted with y times j hat. That's the delta r vector. And when we take that dot product, we get negative E naught times y. Number 25, the potential at the surface of a 10 centimeter radius sphere is 4.8 kilovolts. What's the sphere's total charge? Assuming charge is distributed in a spherically symmetric way. All right, we're going to use the general equation that V of r is kq, k times the charge divided by r. And that's going to lead us to V of r, capital R, being the radius of the sphere, equals kq divided by the radius of the sphere. We're going to solve that algebraically for q. We'll plug in where r is 10 centimeters. We have the voltage at the surface. Divide by k. For k, I've just used 9 times 10 to the 9th. You might want to be a bit more precise and do 8.988. And we should get 5.3 times 10 to the negative 8 coulombs. Number 27. A 3.5 centimeter diameter isolated metal sphere carries a charge. Find the potential at the sphere's surface. If a proton were released from rest at the surface, what would be its speed far from the sphere? Because the sphere has a positive charge, you can see that the proton is going to, as it's released, it's going to fly away, and we want to know its speed when it gets a very far distance away. So here's the setup. We first of all have voltage equals kq over r. So the potential at the sphere's surface, kq over r, and you should get 442 kilovolts. For part B, we have the, here's the sphere, here's the little proton right here. Let's take it at 2 points, point A and point B, which is very, very far away. The potential difference from A to B, the change in potential difference rather, is the charge times the voltage difference. The charge is E, and the voltage difference going from A to B is the potential of B minus the potential at A. The potential at B, a very, very far distance away, is 0. So that leaves us with just E times negative the potential at the surface. We've already calculated the potential at the surface in part A. So it was negative 442,000 volts. So the change in potential energy is going to be negative 442,000 eV. And we can convert that to joules. We'll need to do that if we want the speed. So its change in potential energy as it gets to a distance very far away is negative 7.09 times 10 to the negative 14 joules. If we want its speed, we want to solve for kinetic energy. So change in kinetic energy is the opposite of change in potential energy. That's basic conservation of energy right there. So change in kinetic energy is plus 7.09 times 10 to the negative 14 joules. Solve for velocity. Now be careful with v's here. This is a lowercase v, meaning the speed. This is not potential. V squared is 2 times the change in kinetic energy over mass, where the mass of the proton is 1.67 times 10 to the negative 27 kilograms, and we get a speed of 9.2 times 10 to the 6th meters per second. Number 31, the electric potential in a region given by the equation find the potential and the components of the electric field at the point 1, 1, 1 meters. Well, here's the equation that is the potential. So part A, pretty easy. We just plug in x equals 1, y equals 1, z equals 1, and we get the potential is 2 times 1 times 1 minus 3 times 1 times 1 plus 5 times 1 squared, 2 minus 3 plus 5, and we get 4 volts. For part B, if we want to know the electric field, the components of the electric field, we're going to use this equation. The electric field is the negative of, we're going to do the partial differentiation for the vector components, the derivative of voltage with respect to x in the x component, voltage with respect to y in the y component, and voltage with respect to z in the z component. We do that differentiation and we should get v with respect to x will give us 2y minus 3z. V with respect to y will give us 2x plus 10y. V with respect to z gives us, right here, negative 3x. So there are their components. Now we're going to plug in x equals 1, y equals 1, z equals 1, and we get negative 1, 12, and negative 3. So here is the answer as it was asked. What are the three different, the x, y, and z components? We get 1 volt per meter, negative 12 volts per meter, and 3 volts per meter. One thing I forgot to mention, remember there's this negative sign on the outside. So it's the negatives, the negative distributes, and that gives us positive 1, negative 12, and 3. Number 41. A 5-gram object carries 3.8 microcoulombs. It acquires a speed when accelerated from rest through a potential difference v. If a 2-gram object acquires twice the speed under the same circumstances, what is its charge? So here I list out all the information. For particle 1, we'll just say V1 equals V as it was given in the book. Particle 2, Q2 is the unknown. V2 is just 2 times V as defined in the book. We recognize that change in kinetic energy is the absolute value of change in potential energy, is the absolute value of QV. I'm using absolute value instead of invoking the negative signs just because really that's all I care about. What is the positive value of these things? So 1/2 mv squared equals Q times potential. Be careful with your V's. We have a lowercase v for speed and a capital V for potential, which means that mv squared over Q equals 2 times potential. And that potential is going to be constant for both particles. So what I've done here in this line with the asterisk is I have moved everything that's going to be variable between the two particles to the left-hand side, everything that stays constant to the right-hand side, and so we have mv squared over Q equals some constant. With that in mind, I can then ignore whatever that constant is and just say m1 v1 squared q1 equals m2 v2 squared q2 and solve for whatever it is I want to solve for, in this case the charge of particle 2. So we get q2 equals q1 times the ratio of the masses m2 over m1 times the ratio of the speeds v2 over v1 squared. We plug in all the values. 3.8 microcoulombs, you have the masses, 2 grams over 5 grams. The speeds, 2v over v, the v's cancel out, and we're left with just this part gives a ratio, or a factor of 2 squared. and we're left with 6.1 microcoulombs for the charge. An alternate solution, just another way to solve this. I recommend the way that I just showed, but another way to solve it is from, where is it? I brought it off the page. From this equation with the asterisk, from this equation, you can actually make up a value for V1 and solve for the voltage, solve for the potential. So taking this equation, mv squared over q equals 2 times potential, and let's just make up a value. Let V1 equals 1 meter per second. In that case, you get a potential of 658 volts. And then use the equation that I showed up above and solve it for Q2. You could also do that method. Number 47. We're given an electric field AXI hat, where A is constant, so it's going to be changing as we move across the x-axis. Find the potential as a function of position in the electric field, where V equals 0 at x equals 0. We have electric field equals AXI hat. The potential difference between 2 points from A to B is the negative of the integral, the electric field, from A to B, dot product of E vector and dr. We're going to plug in E into the the E vector is. It's AXI hat dotted with I hat dx. So expanding the left-hand side of the equation, we want to know the potential at x. So we'll say the potential at x minus the potential at 0. Oh, I've already done these limits of integration from 0 to x. The potential at 0 is defined as being 0. So we get the potential at x is the negative of the integral from 0 to x. And when we take this dot product, two vectors both in the same direction, it's going to be their magnitude, so ax dx. So we take that integral. We get the a can go out to the side. We get negative a over 2 x squared taken from 0 to x, and you should get negative 1/2 ax squared. Number 51 involves two charges, one a positive q at the origin, the other negative 3q at x equals a. Find 2 points on the x-axis where v is equal to 0. Here's the diagram right here, 2 points where v is equal to 0. Potential difference when, potential when we're dealing with several different point charges is going to be the sum of each of them, so k times the charge divided by distance. So for the first charge, kq over the x value. X is where wherever on the x value the point we're looking for is. Now it could be on the negative side, it could be on the positive side, so we have to allow for that it could be negative or positive. So we're going to say over the absolute value of x, meaning whether it's at x equals 5 or x equals negative 5, we want to take that distance as 5. Plus, we have k times negative 3q divided by, and we want its distance, the point's distance from A, whether it's on the left side or the right side, and that's going to be the absolute value of x minus A. When we add these two potentials up, they're going to equal 0. So now we simplify. We can factor out k, we can factor out q, they will divide out, and we're left with 1 over x, 1 over the absolute value of x equals positive 3 over the absolute value of x minus a. Where this positive came from, just keep in mind what I did. It was negative when it was on the left-hand side of the equation, but then I added it over to the right-hand side of the equation. Solving further, we get 3 times the absolute value of x equals the absolute value of x minus a times 1. So this is the equation, this is what it's reduced to, and we need to solve this, dealing with the absolute values. So, as I wrote, there are 2 ways to handle this, 2 different solutions, but keep in mind, this is what we're going to solve for now. 3 times the absolute value of x equals absolute value of x minus a. Okay, solution number 1. You'll find that solution number 2 is a bit shorter, but let's do this one first. We have to take the 3 different regions. One where x is on the left of 0, one where x might be between 0 and a, and one where x is on the right-hand side of 0. And we have to consider each of those because the absolute values will take different values. Let's take the region on the left where x is less than 0. 3 times absolute value of x becomes 3 times the opposite of x. Equals absolute value of x minus a becomes the opposite of x minus a. In that case, we have negative 3x equals negative x plus a. We get x equals negative 1/2 a. There's our first answer. Our second region we have to consider is if x is somewhere between 0 and a, meaning x is positive. In that case, 3 times the absolute value of x is 3x. The absolute value of x minus a, if x is less than a, is a minus x. If x is less than a, then x minus a is going to be some negative number. We take the absolute value of that, and we get a minus x. In this case, 3x equals a minus x becomes 4x equals a, and we get x equals 1/4 a. The third region we have to consider is assume that x is greater than a. Well, in that case, 3 times the absolute value of x, remember x is going to be positive, so that's 3x, equals absolute value of x minus a. If x is greater than a, that's positive, so it equals x minus a. So these absolute value signs just simply go away in that region. And we get 3x equals x minus a, x equals negative 1/2. Yes, okay, solving it. Okay, x equals negative 1/2 a, but that's not a solution because x, well, if a is positive, then x is that's gonna make x go negative, but x is greater than a. So that's not a solution. That's one way of solving this problem. The second way is the way that I prefer. You can see it's much shorter. I think it's much more straightforward. And it's this. We start with the original equation, 3 times the absolute value of x equals x minus a, absolute value, and we square both sides of the equation. And in the process, we get 9 times x squared. Doesn't matter whether x is negative or positive. When you square that, it's just going to become x squared. Equals x minus a squared. I'm going to expand that out and show it to be x squared minus 2ax plus a squared. I solve this. I get 8x squared plus 2ax minus a squared. That can factor to 4x minus a times 2x plus a, and I get x equals 1/4 a and negative 1/2 a, which is the same answer I got from the first solution. Number 58. Number 58, the potential in a region VAXY where A is a constant. Determine the electric field in the region. Sketch some equipotentials and field lines. All right. So we have V equals AXY. We're going to take the electric field is the negative of, and we do this partial differentiation with respect to X, with respect to Y, with respect to Z. Don't forget this negative sign there. So with respect to X, it's AY. With respect to Y, it's AX. With respect to Z, it's 0. And so here's the vector notation. The equipotentials are, if V is AXY, we want to sketch all the places where voltage is the same. And I want you to see this, that it is constant X times Y. V over A equals X times Y. And that takes the shape of these inverse relationship curves. So high potential would be up here, medium and low potential would be right there. The electric field is going to be pointing towards the negative I hat and negative J hat direction, so generally going in this direction. And remember, electric field is always going to be perpendicular to those equipotentials. And so these curves look like this. Number 61. I have two solutions for number 61. One of them, as I wrote here, requires familiarity with spherical coordinates. And depending on your familiarity with spherical coordinates, that's okay. If you're not, then there's also a solution using Cartesian or XYZ coordinates. So I'll do them both ways. When I started this, I assumed that spherical coordinates would be more concise because this is radially and spherically symmetric. That's usually the way to go. Those are the coordinates to use. But when I did it both ways, I didn't find much of a difference of ease. So I'll just show you both solutions. You decide for yourself. 61 says the electric potential in a region is negative V naught R over capital R, where V naught and R are constants. R is the radial distance from the origin. Find expressions for the magnitude and direction of the electric field in this region. Well, here's a picture of it. It's radially, it goes out in all directions from the origin. We have electric field is the negative of, and we do the differentials with respect to X, Y, and Z. Now, we can switch that over and solve this with spherical coordinates. In other words, we can do it with some minor modifications, doing it with respect to R, theta, and phi. I'm sorry, R, phi, and theta. Excuse me. So that becomes the electric field is negative of, and we have the R hat, the phi, and the theta hat directions, and this would be differential with respect to R. We need to make the modification. It's differential with respect to phi, but there's a 1 over R sine theta coefficient, and differential with respect to theta, but there's a 1 over R. When we do those, the differentiation with respect to R plus differentiation with respect to phi, which it doesn't depend on, differentiation with respect to theta, which it doesn't depend on. So these two terms go to theta, and we're left with electric field equals negative of dV dr over, or I'm sorry, times R hat. And so when we take the derivative with respect to little r, move the page down here, we get negative, it's negative V naught little r over big R. So when we do this with respect to little r, we get negative V naught over big R, which is right here. Don't forget your negative sign on the outside, and we're left with V naught big R times R hat. It's V naught R radially going out from the origin. That's the solution using spherical coordinates. But let's look at this solution using Cartesian coordinates. It's a bit messier, but it uses Cartesian coordinates, which you might find easier. So here's the equation for electric field, where V is negative V naught over R times R. And what we're going to need if we're converting with R, but we need to use X, Y, and Z, that R is X squared plus Y squared plus Z squared, and it's the square root of that. Put it to the 1/2. And this is three-dimensional Pythagorean theorem right here. So we're going to need this substitution as we convert from R to X, Y, and Z. So when we take the V with respect to X, I've just written out here, it's the derivative with respect to X of negative V naught R, little r, with respect to Y and with respect to Z. In all cases, we can take the negative V naught over R, throw it to the outside of the derivative, and it just becomes V naught over R times, and the three vector components are dr dx, dr dy, and dr dz. So when we take R with respect to X, and remember, this is R, it's the 1/2 power of X squared plus Y squared plus Z squared, you should get 1/2 X squared plus Y squared plus Z squared to the negative 1/2 power times 2X. When you take R with respect to Y, it's 1/2 X squared plus Y squared plus Z squared to the negative 1/2 times 2Y. Take take R with respect to Z, and you get 1/2 X squared plus Y squared plus Z squared to the negative 1/2 times 2Z. Recognize that in every one of these cases, in every one of these components, you have X squared plus Y squared plus Z squared to the negative 1/2, and that is 1 over R. So the 1/2 and the 2 cancel out. So for the X component, we're left with X over R. For the Y component, we're left with Y over R. For the Z component, we're left with Z over R. So it reduces to this. Remember the V naught over R that we threw to the outside of the vector, and it's X over R, Y over R, Z over R. Let's factor the 1 over R out, put it to the outside, X, Y, Z. The vector X, Y, Z is the R vector. So we have I gone off the page yet? Here we go. X, Y, Z, it's the R vector. So we have V naught big R over big R little r times R hat. I'm sorry, times the R vector. Now, R vector divided by R is R hat. So we're left with the electric field is V naught over R times R hat, which is the same result we got with the first solution. And that is the end of the chapter 22 homework.